Not sure why there's a delay in the servers these days. I'm just waiting for that deet. Maybe because my hard drive's getting full. I don't know. It seems to get longer and longer. Oh, here we begin. Hi guys, welcome to another episode together. And today we're going to move from a straight conductor to a coiled conductor and see what the outcome is. Okay, so just for a bit of background, you don't need to copy this part down, but there is a mathematical equation in predicting the magnetic field intensity through a piece of wire. All right, and the formula looks something like this. Where are you, wire? There you go. There's the formula, okay? B is equal to mu naught times I over 2 pi r. As for the derivation of this, it's beyond the scope of this course, so you don't need to worry about that. And in fact, this slide you don't need to copy down. But what I do want you to know is what the relationship is in our setup. Okay, so this formula will be given to you just as a reference, but you're not going to do any calculations with it. First off, if you're wondering what these units all mean, mu naught is a constant. It's known as the permeability of free space. It's a constant of 4 pi times 10 to the negative 7 Teslas times meters per ampere. We'll cover that in grade 12, right? Just know that it's a constant. It's just a fixed value. I is the current that's passing through the conductor, and it's divided by 2 pi r. Okay, so from looking at this formula over here, I hope you can see the relationship between B and I, right? What is that correlation? What's the relationship between B and I? You'll notice that if I doubles, B will definitely double when you sub the values in. So in other words, they're directly proportionate. So if you double the current, the B field going through the conductor will be double. So that you should know. All right. So you double the current, you'll double the B field intensity. And it's inversely correlated with another thing, which is R. And R is the radial distance away from the conductor. So however many meters you are from the conductor itself. Okay, because the further away you are, the weaker the magnetic field strength. And you're probably used to that with permanent magnets. All right, and the same thing happens with this conductor here. The magnetic field intensity is very strong near the conductor, but it becomes quite weak on the far end. And when you look at this formula over here, B and R, they are inversely proportionate with each other. So that's all you really need to know about this formula over here, that the B field intensity is proportionate to current. So if you double the current, expect the B field to be twice as strong through the conductor. And the further away you are from the conductor, the B field intensity will drop. So that correlation you need to know. The math behind this, you don't need to worry about so much. But if you're curious, here's an example. Okay, what is the B field intensity when you are 2 centimeters away from the conductor and you're allowing about 2.5 amperes to flow through this, which is probably the maximum amount of current that will flow from a AA cell. So you take a AA cell, you connect it to a wire, and you let it run. It's going to get piping hot because there's 2.5 amperes passing through it, and you're curious about what the B field intensity is over here. One thing to watch out for is that current needs to be measured in amperes. So that's the same thing as 2.5 amperes. And distances, as before, is always in meters. So make sure you convert that into 0.02 meters for your R for radial distance. So sub everything in, crunch it through, and yeah, you're going to get a tiny number. You're going to get something to the negative 5 Teslas. As I said, the demonstration I normally don't show students because other than a bunch of smoke, you're just using your imagination trying to see the concentric circles. It doesn't work very well with the equipment I have here. All right, so that's why I just forego on that demonstration. I'll show you another one that's really cool that does prove everything. Okay, but right now just know that, yeah, it's going to give you some value that's very low. And if you're wondering, you know, what exactly is a Tesla? Well, if you have a very strong magnet like, oh dear, I don't know if you ever played with these ones before. I have it on a sweet spot. Oh, I ripped off some of my plastic too because it was right beside it. But these rare earth magnets are pushing 1 Tesla. And you can see the Tesla outcome even from a distance. You can see that's causing my field magnet to spin around right over here, even at a long distance away. In fact, I think at even 50 centimeters, I can influence, and look at that. Look at that turn. Oh, yeah. Right. That thing's turning even from that far away because of me flipping this around. Okay, so these are very strong. So if you're at the surface, this is pushing 1 Tesla. All right, so if you're curious on what 1 Tesla is, one of these rare earth magnets, if you have a chance to play with them at the surface level, is pushing 1 Tesla. All right, so everything else outside would be less than 1 Tesla, including your ordinary run-of-the-mill magnets. So if you have these little cheapy ones, they're only about 1/10 of a Tesla, and that's why look how weak that is. It just fall right apart. Okay, so that's about 1/10 of a Tesla there, and a strong one is pushing 1 Tesla. So this could be anywhere from 100th to 1/10 Tesla, and 1 Tesla is that thing. And if you ever gone for an MRI machine, it gets as strong as 3 to 5 Teslas. Okay, so if that's strong, well, then when you go in the MRI machine, it's 3 to 5 times stronger than what that is. And that's why when you go through an MRI machine, they will always make sure that you have no metal on you, because if there's any metal on you, you're not allowed in the machine whatsoever. They need to have a different plan of attack and diagnosing your body. In fact, one of my colleagues, he had to go for an MRI exam, and what did they ask him? They asked him if he was part of the trade business and if he's done any welding before. And he looked at them funny, wondering, why do you want to know such personal information? And yeah, apparently he did do that stuff in his earlier career. And as a result, he could not go for an MRI exam, because their concern is that if you are doing any form of welding and you weren't wearing your welding glasses, there's a chance there's a shard of metal that got caught right in the cornea of your eye. Yeah, it's itchy. You didn't notice it, but that was it. And you can imagine the danger of you going into an MRI machine with even a speck of metal. It's just going to rip right through your eyeball, and then you'll become blind just by going in the machine. Okay, so they'll ask you crazy things like that. Anyways, that's all I wanted to explain over here. What a Tesla was. Now you know. All right. When you end up hitting 1 Tesla, it's pretty strong, and anything beyond there, you're in an MRI machine. It's ridiculously strong, where they can't even put chairs in the same room, because if they had a chair even 10 feet away, it's going to roll right to the machine and then destroy both items. There's YouTube videos on that. Okay. Now, that's with the straight conductor. And as I said, with a straight conductor, the B fields emanate around the conductor. And yeah, it's going to be very weak. It's not going to be all that exciting. All right. So to make it more interesting, why not just take the straight conductor and start looping it around like so? And let's analyze in this picture what's going on. All right. So we have a loop that looks something kind of like this, floating in space right now. And if you observe the current is coming in from one end. I'm trying to simulate what it looks like on your screen. So what am I supposed to do? So hold it like this and hold it like this for you guys? Yeah. All right. And the current is going in through the back. And as it goes through the back, you can see that if you use your right-hand rule, the B fields go up through the middle of this curl. Okay. In fact, over here, the B fields still go up. And when my current's going this way, my B fields are still going up. So the entire journey of that current as it's cycling through, you can see the B fields are continuously pointing upwards, like in the diagram. And then that starts resembling something that we've seen before. Doesn't this look kind of like this? Okay. So that's the cool thing about this setup over here. It starts to resemble this picture over here. And that's just with one loop. Well, take that idea now. Okay. You have one loop. And your one loop is forcing all your B fields all together. So it's all behaving as magnetic north over here and returning all back as magnetic south. What would happen to the setup if I decided to flip another loop around? What will happen to the intensity? One loop to two loops. Logically, the intensity will increase, or mathematically what? Double. Good. And if I flipped another loop around here in the same setup, the intensity will triple. Good. And that, my friends, is the introduction towards what a solenoid is. A solenoid is nothing more than just a piece of wire wound it around plenty of times, and you created a solenoid. Solenoids are effective at creating a very strong magnetic north domain and a very strong magnetic south domain, or pole, sorry, in a setup in space that's temporary. All right, it's not permanent. Okay, so again, this is a formula that you don't need to copy down, but again, this is just emphasizing that yes, the B field intensity is proportionate to the value of I. So you double the I, the B field will increase, and it's inversely proportionate to the radius. And that's why with regards to solenoids, you want to make them nice and tiny like this. All right, you want it to have a very small diameter. Therefore, you're squishing all the B fields together at the center, making a stronger solenoid. Okay. So then here's a text that, yeah, if you want to copy down, you're more than welcome to, which states this. The B field intensity can be increased by placing a greater length of conductor within a confined area. Best way to do that is to start coiling it up. The conductor is coiled up to allow the exterior B fields to all flow in the same direction, and the interior B fields to also flow in the same direction as well, making a much stronger and more efficient magnet, or electromagnet. I'll give you guys a moment to jot that down, and then I'll show you some demonstrations to prove that this stuff actually works out. Okay, hope that's enough time right now, because the next part is to show you all these crazy demonstrations that this stuff does work out, right? So I'm going to switch over to camera view of a solenoid. Now, it's not going to look exactly like this because it's all compacted together. Instead, I'm going to spread it out, make it nice and big. It won't be as strong or as effective, but it'll get the general idea across. That's all. All right. So here's the camera view. Okay. So here is my three-dimensional solenoid, and you can see that the coilings go through this plexiglass over here. That way we can see how the B fields look like, at least when we take a little slice from the center over here. So I'm going to sprinkle some iron filings on top, and I'm going to see if there's any resemblance of any sort of pattern with the setup. Okay. Now, again, electricity is colorblind. It doesn't care what color the wire is, but just to keep to a standard convention, we always like to use red as our positive and our black as our negative. Again, back 300 years ago, they had no idea which way current flowed from. Was it from here to here, or was it from here to here? So they just made an assumption and assumed that current flowed from red to black, or from positive to negative, because they observed the same exact outcome as our setup over here, and it could be used to predict the direction of the magnetic field. And here's my compass to show it. Okay, so I'm going to keep a compass in the vicinity. Hope that this is zoomed out enough. Maybe I'll zoom it out just a little bit more. Is it in focus? There it is in focus. And just to let you know, in this setup over here, and I don't know why it's pointing that way. I didn't even turn it on yet. Where's my permanent magnet? I don't know what's going on here. Okay. So this should point to magnetic north. That's correct. And this side should point to magnetic south. And this is messed up. Something must have become magnetized. Oh, the tip was magnetized, wasn't it? Yes, the tip was magnetized at some point. Okay, I think that's good. So this must be, yeah, look at that. Look at that. That's magnetized. That's ruining my setup by this guy over here. All right. So normally it should point this way, but you know what? The best way to do this is to just tilt this like so. That way I can neutralize whatever else I have here that might be influencing my answers. Because in this setup here, what I'm trying to do is I'm trying to show you that this side can either be magnetic north, where the south pole will face towards it, or this could be magnetic south, where the north pole of this compass will point towards it. So the blue area actually indicates magnetic north. That's how I magnetize it right now. Okay, so north is here, south is over here, and I haven't done anything yet. So I'm going to plug it in. And yeah, I am using an insane amount of current. All right, if you don't believe me, here's the craziness. Hey, why aren't you lighting up? It's because I didn't plug it in properly. Because if I did, you'll see sparky spark. Look at that. Okay, I'm using an insane amount of current just to do this demonstration. So it will smoke up and it will stink in my basement laboratory. All right, so I'm going to turn it on, and then I'm going to start sprinkling some iron filings on it. I'd love to play that song for you guys because this is the most appropriate time for it. But seeing I'm going to get a copyright infringement, I'm just going to butcher up the lyrics, and hopefully they will not, they will not ding me for that. Because what you know about rolling in the deep, and there you go. That was terrible. Let me just redo that again. Oh, stage fright right there. Okay, let's do this one more time. And two things you'll notice. First off, you'll see that this is pointing towards it. And number two, if you look really closely, you'll start to see that there are lines in the center. Yes, no? Oh man, I got some filings in my keyboard now. Oh, all for the love of science. Okay, so yeah, this crazy thing does happen. All right, that when you pass current through a solenoid, you will force all the B fields to all congregate together and separate on the other side. Now here's the question: does it come in like this, or does it come in like that? And really, we can't tell. The only way that I can really tell is by taking each and every single one of these iron filings and coloring one side red and one side blue, and then putting them all in here. So that if we zoom in enough, we can start seeing it. And that's difficult. We're not going to do that, okay? And that's why I had this little tracer over here. And if you notice, this started pointing this way. And so if it points this way, then it's telling us that this side must be magnetic south, all right? So this side over here is magnetic south, and on the far end, it is magnetic north. So we have south on this end because the north pole pointed towards it, and logic dictates that this side over here is north. So what's really happening is that the B fields are leaving from the top and returning back to the bottom. and cycling over and over and over again. Okay. Oh, what a mess. Okay, so let's go in and try to prove that, yes, it's going to be south on this side and north on the opposite end. Okay, so here's a picture of what happened, and I guess it's flipped the other way around. Oopsie daisy. Okay, because again, if you look at my video setup, you can see that I had my red on the bottom and my black on top. So really in this thing over here, it's just the other way around. Yeah, so really it's just taking this and flipping it that away. Oopsie daisy, I should have paid attention to that first. But this is the outcome you would have seen anyways. Okay, if you flip it around like this, you'll see that the compass will flip this way because north loves south. All right, and that's what would have happened in the setup. You know what? Why not? I mean, oh my gosh, I'm getting iron filings everywhere. I may as well just prove that to you right now because that's quick. I'm just not going to sprinkle any more filings all over my desk because this is messy. This is messy. We're doing this all for the love of science. All right. So once I end up hitting that button, you can imagine the song in your head because once I say the word deep, this is what you'll expect. Don't stick there. Stick. Oh my gosh. That's kind of disproving my theory. So you know what? I'm going to plug it right here just so that we can confirm for sure that this is the outcome. And there you have it. Okay, so this side will behave as magnetic north, and that side will behave as magnetic south, just like in my snapshot over here. Whew, and there's some smoke. Okay, can you guys even see the smoke on video? Oh, there's smoke. I guess you can't see on the video, but trust me, it stinks down here. Okay, so let's stick with this picture up here. I'm going to switch my casting to, I don't know, maybe you can see my face instead. All right, and let's go and oh, that was hot, and explain why this picture looks the way that it does. Okay, so again, we have our current flowing from the top up here. Okay, because again, that's where the positive lead is. And as the positive lead comes down, we have our current sticking out through the right-hand side. So it comes out on the right-hand side, travels up and down on the left, like so. Then I'll go down through the plexiglass, go up all the way around again, and become a dot yet again. So we have X's all on the left, and we have dots on the right, like so. Now I'm just going to remove the background so we can see that this is what we're up against. Okay, and then I'll bring that picture back so you can prove to you why it is what it is. Okay, now there's just too many X's and dots here. I could draw them out, but it'll just take too long. So I'm just going to skip to every second one. That's all. Okay, and again, I'm only skipping just for time efficiency. You could go off and draw all the circles for this and come to the same conclusion. All right, so with regards to the X's on the left-hand side, we're going to use right-hand rule number 1 again, or Oersted's principle. X means that you're going to stick your thumb right into the page, or in my perspective, I'm pointing it this way. And then when I'm drawing it, I'm going to see that I have B fields that are going to circle around clockwise like so. Okay. Now, in the interactions between the middles of these two, you'll see that the B fields are going against each other. Okay, so what ends up happening is that really, when you look at the end of what's happening in the middle, they get canceled out. So the smaller circles, which I'm going to start off with, I should have started with smaller circles. Okay, the smaller circles, they're still abiding by this right-hand rule number 1, where the B fields are traveling, at least from our perspective, clockwise. But the mathematical outcome of the next ring is that they will cancel each other out, as I explained. Because again, you have a B field that's traveling towards the right, and you have another B field traveling towards the F, and what we're looking at is the outcome of it. I'm sprinkling the iron filings on top, and right and left will cancel each other out. So what we end up having is something that looks kind of like this. And just follow along with me here. Some people are wondering, should I copy this down? I'll leave that up to you, but I just want you to see the overall picture, because this is more of an understanding of why does right-hand rule number 2 work. I'm getting to right-hand rule number 2, okay? So this is the theory behind it. We're just using right-hand rule number 1, what we've learned so far, and I'm just going to expand upon it. Okay. Again, mathematically speaking, those start canceling each other out, where at the end of the day, you're going to see this really long, elongated oval. And that's it. In fact, I'm going to stop there. I think that's enough there. Okay. Now I'm going to rinse and repeat on the other side, and I'll color code it differently just so that you can see that I'm doing the other side. Okay, so this time around there's a dot, so the dot's going right to your eyes, and as a result, the B fields will curl like this. So it's going to curl counterclockwise. I'll start with the smaller one. Okay, so counterclockwise, all of them will. And the interesting thing is the next ring. Okay, in the next ring, again, they're going to mathematically cancel each other out right at the intersection there because they're opposing in direction. So our next ring will start looking kind of like this. So they're still tag teaming together. So on the outside, they're all traveling the same way, but inside they're canceling out. And it's just going to keep on averaging itself out to start looking like this. In fact, this looks just like that, doesn't it? Okay. And in fact, as we described, the B fields, they leave from the North Pole and they return back to the South Pole. And as predicted, that is the outcome from our setup. There you go. There's the proof. Okay. Now, the proof that I'm doing here, you can see that it took quite a while, right? I spent probably 2 to 3 minutes trying to prove that this side here will be north down below, and up above, it will be magnetic south. But there is a much faster way of getting to the answer, and it only takes about 3 seconds. And that is right-hand rule number 2. Right-hand rule number 2 states this. Take your lovely little fingers. Your fingers will indicate the direction of current that's flowing through the conductor right over here. So in this setup over here, if this is the positive end, we're going to have our fingers go up through the front, like so. So as the fingers go up through the front, our thumb goes, good job, North Pole. And if you look at the setup that we have here in the video, it's exactly the same as our outcome. Positive on top, negative down below. Our thumb points downwards, telling us that North Pole is at the bottom. Okay, so some want to take a look at the previous picture. By all means, this is what the previous picture looks like. All right, and it's just for your reference. Remember that this is all being recorded, so if you really want to rewind back and take a look at it, you can. But the typical grade 11 student will really just move on from right-hand rule number 2. So this is the story of why right-hand rule number 2 gives the answer that it does. All right, but for our speed and efficiency, as you can see, I could already predict the answer of where north and south is just by using my hand. Once again, right-hand rule number 2, and you'll see it written on the next PowerPoint slide, is that your fingers indicate the direction of current flow. So if this is positive over here, it's going to flow this way out through the front. So that's why my fingers are going to point to the front. And as they point downwards to the front, they go upwards to the back and eventually exit out on the negative end. And in doing so, in this setup over here, my thumb always goes and points to, good job, North Pole. Okay, so that's why North Pole points out over here. So according to the setup that I had over here, we had it set up like this. So if I rewind back, there you go. Positives on top, negatives down below, and this is pointing down below. Now, guys, just watch out. Don't assume that the minus sign and north are pointing in the same direction. Okay, a lot of people think that that's the case, but that's not always the case. That's just the setup based upon how I have it set up over here. Okay, so once again, with right-hand rule number 2, because people are asking me to say it again and again, I have it all written out. Here it is. Fingers curl in the direction of the current flow, and your thumb points to wherever north is. And this is right-hand rule number 2, and that's the quick way of getting to the answer. Now, if you're wondering how in the world do you draw these pictures over here, best way of drawing it is you'll have this thing which represents your solenoid or your tube. And you can see that right here, you start from the left-hand side and going up and around. So that's what you're going to draw. You're going to draw a little fish hook that looks like that. And then from there, you're going to try to imaginarily extend that where that end of the fish hook is, and then continue on with these letter S's afterwards. All right, so this is Art Class 101 with Mr. Nee, and that's how you draw it. All right, for the second one, you're going to do something similar as well. You can see that it starts entering in from the front and the back, and it goes downwards, up through the back, downwards, and this is how you draw it in your notes. And it's going to exit through the back, just like this one over here. It's going to exit through the back. Now, as for the last one, you'll notice that in the last one, you start off from entering in from the back, and you go out through the front. So you're really drawing your S patterns the opposite way around. Try to keep them uniform. I know that I'm kind of rushing through this, so they're not perfectly uniform. But if you're careful enough, that's how you draw it by hand. Always got to clean up after you're done with a demo, and this is one of the messiest demos around. So I got iron filings everywhere. I hope it hasn't ruined anything down below. Yum, yum. Yum, yum, bubblegum. Okay. So now let's start predicting which side will be magnetic north and which side will be magnetic south based upon our setup here. Okay. So in the first diagram, we see that current is going up through the front. So then you can start placing your hand on top of these solenoids, all right, where your fingers point in the direction of current flow. So it's going up through the front and down through the back, like so. Okay. And as you have your fingers going up through the front and down through the back, look at where your thumb is pointing. And you'll see that your finger is pointing to, good job, North Pole. So on the left-hand side, it'll be magnetic north, and on the right-hand side, logically, it'll be magnetic south. And that's how you answer these questions over here. I gotta bring out the vacuum later on because this is nasty. Black dots everywhere, but they aren't sticking because they're not ferromagnetic. That's just dirt on the ground. Again, we reuse this stuff year after year. So over time, I am picking up random debris. Okay, I hope that gives you enough time in solving the next few. So if you know that your thumb is magnetic north, that means that the back of your wrist is magnetic south. And that's how you're going to be setting up in this diagram. South on the left-hand side, north on the right-hand side. And you can see in this setup over here. And yeah, maybe it is nice to have some paper toilet rolls around so that you can help yourself figure out what's going on. Okay, so south is where the base of your hand is, and north is where your thumb is pointing. And you can see that in the setup over here, your B fields need to be pointing downwards. Okay, at least through the front of the setup. So in this setup over here, I have, not B fields, sorry, your current. Your current is pointing downwards through the front of the tube, meaning it's going up through the back, or the current is going up from back here. So it's exiting down on the left-hand side, and it's entering in from the left-hand side. Student has a question.
Sorry. I'm just confused. Why is the current moving that way? Why can't it be moving the other way?
It's not that it can't be moving the other way. It's just that if you move it the other way, then the magnetic fields will be the opposite way around.
So how do you know which way it's moving?
That's why you use right-hand rule number 2.
No, but
now in these problems over here, if you're asking, how did I know that I was going that way?
Yeah.
Erase all of this. It's because this is what's given to you on the test. Because if I didn't give you an eye over here, you wouldn't know the answer. Hope that answers your question. I have to give you a hint on something. I either have to tell you which side's magnetic north, or I have to tell you which way the current is flowing. Because without giving you that subtle hint of information, you won't know which way is is north or which way is south.
Oh, you told us which way was south. Oh, I didn't see that.
Oh, well, in the second and third
Yeah, in the
example.
second one. Yeah, okay. I didn't see that.
Yeah.
Okay.
In the
Now,
first example, all I told you was the current. All right. So once again, since I've already erased everything, if your current is pointing upwards, you take your hand and you allow your hand to point upwards through the front of the tube. And that tells us that to the left is where magnetic north is. So that's why north is on the left-hand side and south is logically on the right-hand side. In the second example, this time around, we have north pointing towards the right. And with north pointing towards the right, you can see that your fingers are now pointing downwards through the front of the solenoid. Yeah, it's going up through the back, but it's going down through the front. All right, so at the front, you'll be drawing all these down arrows. And if you follow the path of this treasure trail, it'll tell you that the current exits on the left-hand side and enters in from the right-hand side. Okay, so the answer key is based upon at least one of the givens. Okay, yeah, unfortunately, once I erase, and that's why I'd rather go linearly as opposed to jump back and forth. Once it's gone, it's gone. But again, that drawing over there is identical to what you see above. This is just how you draw it by hand yourself if you were to draw it out. Okay, so the first one would look like this. The second one would look the same. South is on the left, north is on the right. And again, if you use the right-hand rule, you'll see that the B fields go up through the back and down through the front. So you'll be drawing all the downward arrows afterwards. And then lastly, you just trace the path of the arrows. So this tells you that the current's going to exit out of the left, and the current is going to enter in from the right-hand side. So between these two diagrams over here, they do look almost the same, right? In fact, they are arguably speaking the same solenoid, right? The setup is exactly the same, but you'll notice that the moment I change the direction of current flow, right? Because if you look at the example on the left, current enters in from the left-hand side, and the example on the right, the current's entering on from the right-hand side. Just by doing that, we have affected the directions of the poles. You can see that they're facing the opposite way. All right, so by just flipping the current around, you will be affecting which side is north and which side is south. I also mentioned to you guys, please don't memorize current and north pole or current and south pole. That's not the answer. The proper answer is using right-hand rule number 2. Because in the third example, the diagram looks very similar, but however, if you look at the direction of coiling, now it's entering in from the back and exiting out through the front. Okay, when you look at it from left to right. So it's coiled the opposite way around. In other words, the outcome of this setup or this experiment will give you the complete opposite answer. All right, so south is still on the left-hand side, north is still on the right-hand side. You take your toilet paper roll, hold your hand as necessary, and this time around, yes, the current is going down through the front. So we have arrows pointing down through the front. However, this time around, it exits out on the right-hand side. So you'll notice that even though the poles of this example here in the middle versus the example on the right, the poles are still pointing the same way, the current now is the opposite way, and that's because the direction of coiling has changed. Okay, so yes, be mindful on how the drawing is done. That will impact your answer. Any questions? Okay, other properties, and I'm going to start erasing all of my extended drawings now. All right. So north, down, 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 up from here, out, down there. There we go. I need to erase all of mine so that you can see all that text. And yeah, I'll give you guys a moment to jot down the text, and then we'll reemphasize what it all means yet again. Give you guys 2 minutes to work on that. No, I'm not going to spend 10 minutes on it, or sorry, 5 minutes. Instead, I think 2.5 minutes is enough to get the idea across. It's just that my timer is only set for that time. Okay. All right. I just made a mess when I cleaned it up. That was not efficient. Not efficient. Okay. So back to this setup again, because I want to prove to you guys that all this crazy stuff here is valid and true. Okay. Now, for the first one, I hope that you intuitively see it, because for me to demonstrate it, that means I need to have a power supply that I can control and regulate the current with, which I don't have here, right? But believe it, if I double the current, then the B field intensity will double, all right? So magnetic field strength is not based upon voltage, it's based upon current. That's one thing to keep in mind, okay? So as the current increases, yes, my B field strength will increase linearly, okay? You can't get more out of what you put in. Okay, so you put in a certain amount of effort, you're going to have a certain amount of outcome. And if you double your effort, your outcome will be double the amount. So I hope that first part makes sense. And the second one, I hope it makes sense as well, where if you take a conductor and you coil it with twice as many loops, it's going to be twice as strong. You coil it with 3 times as many loops, it's going to be 3 times as strong. And as you keep on coiling it, it's going to get stronger and stronger and stronger, because you're squishing all the B fields together. Remember, for a very strong magnet, you're going to have a bunch of B fields all wanting to release from the North Pole all at once, because they're all heavily compressed together. And the best way to squish them together is by reducing the size of your diameter of your solenoids. Keep that small, okay? But here's the other thing you got to worry about. This setup over here is terrible. And it's terrible because I did not compact all the conductors together. You can see that I spread them out. And as I spread them out, it's very hard for the B fields to all confine together and work together all in the same direction. All right. So what you want to do is that you want to avoid spreading out your solenoid like this. Instead, you want to try to squeeze all of the coilings as close as possible together. Can you stack them on top of each other? Yeah, you can. Okay, there's nothing wrong with stacking them top, but you want to wind as many as possible and squish it as narrow as possible. Because the more loosey you put it, the weaker the solenoid, and the closer you put all the coils together, the stronger the solenoid. Okay, so far I've explained 3 of these concepts. Okay, you double the current, the B field intensity will double. You double the turns, the B field intensity will increase. You let it be all loosey-goosey like this diagram or the setup over here, and it won't work as well. If you really want it to work really well, try to squish it as close as possible together. All right, it's kind of like my solenoid right over here. Right, it's not the best of examples, but I did try squishing it together. In fact, to make it even closer together, you want to lose the jacket. All right, with this wire over here, this is a copper wire. There's a jacket that's probably the same thickness as the wire itself. I don't know if it turns out very well on camera. All right, maybe I'll switch over to the other camera view so you can see it. Okay, so if you look at this wire over here, you can see that the jacket is relatively thick compared to the wire itself. You want to try to minimize it by using this special type of wire called insulated copper wire. All right, here's the part that's already been scraped off. I don't have an X-Acto knife with me, but with the X-Acto knife, I can just scrape off all of the oxidized layer, and you'll see that there's some shiny copper right there, and the jacket is not much thicker. All right, this is called insulated copper wire. Some people call it quote-unquote magnet wire, but trust me, this is not magnet wire. A magnet is not attracted to copper whatsoever. Okay, it won't stick to the magnet. Okay, so it's just copper wire that has a very thin jacket, kind of like if you have nail polish on your fingernails. Instead, they use that same nail polish called an enamel, and they coat this with that enamel. Right, so it's an insulator. That way, you can pack it as close as possible. So yes, this is a much more efficient solenoid than this example here, which is much more efficient than this guy over here. Now, to describe that last concept, as the permeability of the core material increases, the B field intensity increases. That's why I want to show you this last demonstration. All right. So right over here, I have a solenoid, but if you look through the solenoid, it's just a completely empty tube. That's it. If you can even see it properly. Hopefully you got to see that. Okay. There you go. It's a clear tube. Okay. Let me just change my camera view so you could see it on the big screen. There you go. Okay, just so you can see on the big screen. It makes it easier for me too because I can point the camera properly. Okay, so you can see that it's an air core in here. And air is one of the worst cores that you can use as a solenoid. I mean, there's stuff worse than that, but it's pretty bad. All right, it's as bad as free space. In other words, if you go into outer space and you have no air particles in there, it's about as bad. All right, so it's not going to work very well as a solenoid. It will work, trust me. If I hook this up right now, it will attract iron filings. No problem at all. In fact, I got to do another demonstration or another fix-up because I noticed that with this guy over here, during my whole tidying up, I kind of messed it up, and now it's become slightly magnetized. So I got to demagnetize it first. Whoops. Is that right? Nope, I hooked it wrong. There you go. Oh yeah, that feels demagnetized. Okay, so let me rewire it properly. I know you can't see it off camera, but to the left I have my power supply. Here's the lovely power supply right here. Yeah, I can keep it at the edge of the camera just so you can see what's going on. Okay, so I have it plugged in to the DC common, and I have it hooked up to 12 volts / 6 volts DC. And right now it's at 6 volts DC, 10 amperes, because again, it's current that dictates whether this will work or not the voltage. Okay, now it is proportional to voltage because this wire here has a resistance. So if I double the voltage, then the current will double. That is true, all right? But then it'll get twice as hot faster. So that's why I want to keep, I want to limit things, okay? I don't want this to overheat because it does hurt the fingers, okay? And yeah, I'll need a tracer. So welcome back to the iron filings, okay? And again, with regards to this screwdriver I have over here, it's completely demagnetized. You can see that the iron filings are not attracted to it whatsoever. Let me just sharpen the image. There you go. All right, so you can see that it's not attracted to this whatsoever, okay? But it is ferromagnetic. If I place a permanent magnet on here and I swipe it enough times, it will become magnetized, okay? So this is a strong ferromagnetic core, but right now it has not been magnetized yet. I'm gonna keep that aside. Okay? No magic tricks over here. Here I have a solenoid where the moment I turn it on, it will cause the iron filings to become attracted to it, okay? So here we go. I turn it on, cue the music in your head, and there you go. And then I'll play the Oh No song because look at that. Barely any was attracted. In fact, there's the comparison. That's all I picked up in this copyright. Yep, no problem. Okay, copyright law in your head. Okay, so what isn't copyright is the outcome of this setup here. As I said, the core that I chose here is air. Air is a terrible core to use for a solenoid. If we want it to be better, we want to choose a core where its magnetic permeability is a lot more than air. If you recall in the previous slide, this will improve it by at least 200 times as it is iron-based. Okay, so let's go and see it improve by 200 times. And you can cue the astronaut song in your head to avoid any copyright infringement. And here we go. And here's the magic. There you go. Pretty neat, isn't it? Okay, and yes, it's going to retain some of that magnetic field because this screwdriver can become magnetized. So if I want to demagnetize it, I can do one of two things. And in fact, there are three things I can do, okay? The one of two things I can do is I can either take this and whack it a few times. Now I have a glass table and I don't want it to shatter, so I'm not going to whack it against the table. If I had a blowtorch in the basement, I could use that to demagnetize this. Or plan 3, which is I take a permanent magnet and I just swipe back and forth really quickly, let's say 60 times a second. One way of doing it is by taking the solenoid over here and converting it from DC current into AC current. So when it's set up in AC current, in every second, it's going to go this way, then that way, then this way, then that way in its B fields, which is enough to scramble this up. So before you can see that it's all magnetized, and after I pass it through here, whoop, look at that, completely demagnetized. Won't pick up a single speck. There you go. Homemade demagnetizer. Now you know, and you can imagine that as the next awesome TikTok video. So make sure you like, click, subscribe, and all the other fun jazz. Okay. So as the permeability of the core material improves, like I've shown you in my demonstration, then yeah, you get a much better solenoid. So here's the mega formula. Beta is equal to mu times Ni over L. Yeah, mu does expand out. You don't need to know this, but mu does expand out to mu r times mu naught. If you recall, mu naught is a constant. It's 4 pi times 10 to the -7 Teslas times meters over amperes. Say that 3 times as fast. Okay, so mu r is a relative permeability. It's just a numerical constant. So if your mu r is at 1, you're just as terrible as vacuum space. If your mu is at 2, then you're twice as good as vacuum space. If your mu is 3, then you're 3 times better, and I hope you get the idea. Okay, so if your mu is at 1, you're just as bad as air or vacuum space. If your mu is less than 1, you make magnetism worse. And if your mu is greater than 1, then you can make a better solenoid. Anyone else still need the slide here? Yes, student has a question. You can type it away or ask away.
Oh, it's just for a slide.
Oh, just hold on. Yeah, I'll hold on. No big deal. I got to clean up this mess. Yet again, I just wiped it down, so that kind of defeated that. Yeah, this is one of those demos where I'd rather do it at school than at home, because I don't like cleaning up afterwards. All right, so please make my efforts here worth the effort. Okay, so after school, make sure you just hit the play button on this video and just watch it from beginning to end, or let your pet dog watch it from beginning to end. It doesn't matter to me. Let the view hours kind of make up for all that effort that's required to make these demos work the way that they do. Whoops, did I hit something? There you go. The third point, can you explain it? The tighter the wire coiling, again, the more you squish them together. You can see that this is all loosey-goosey right now, all right? And when it's loosey-goosey, the B fields, they have a chance to escape right through the middle. So it's not creating a confined B field that's exiting from the North Pole, all right? So it doesn't work as well this way. Instead, you want to make it as tight as possible. In other words, you want the diameter to be as short as possible, okay? So you wouldn't let it loose like that. You'd squish it together so it'll be nice and compact. As another demonstration, I do have other solenoids around, so let me just grab it. Okay, so here I have another solenoid, and this one's much better for two reasons. First off, you can see that the coil turns are all pushed a lot closer together. That's one reason why it's better. Number two, there are way more turns in here. This thing is ridiculously heavy, and this thing is super light, okay? That's the most I'm willing to do on a glass table, all right? This is pretty heavy. This is at least 1 pound. Meanwhile, this thing is only a couple of ounces, all right? Maybe 2 ounces, and that's it. That's light. This thing's heavy. Now, this is not the best of solenoids, even though it's big. The problem is that these coil turns, look how big they are. Look at the separation, because I'm using a very thick piece of wire. This is excellent for high school demonstrations because I can easily pass, I think, around 5 amperes here, and it'll still be okay as long as I use it for a few seconds. All right, 1 ampere is probably the ideal value for this one. On the other hand, with this one, if you pass more than 1 ampere, you fried it. And that's the problem with this guy here. I only use it just for demonstration purposes to show you what it is, but it won't work anymore. You can see the wire is very thin, and this wire may only allow probably around 1 ampere to pass through it. If you do any more than 1 ampere, you'll make a micro fracture. I don't know where the fracture is anywhere along here. If you look closely, this is very fine, right? From camera view, you can't even see the number of turns over here, all right? Because I'm using something that's about as thick as your hair. Okay, so feel your hair right now. That's how thick this wire is. And I've coiled it around at least 100 times here, maybe even 200. But unfortunately, because of that micro burn, because of that high current, it doesn't work anymore. And it's only good for demonstration purposes, just to show you that, yeah, as long as you make more turns per confined area, you can make this work more efficiently with less current. So this guy can probably only work with around 100 milliamperes and it'll work just fine. Diameter here is small, diameter here is very small. And if I throw in something that's ferromagnetic through the center, like a screwdriver, it will make a really good solenoid. Okay, but it wasn't me. I think it was another teacher who fried it by accident, and now it's just for show and tell. This one here still works, and I will demonstrate this in a future episode. So make sure you like, subscribe, and all that fun stuff. Okay, I hope that's enough time for this slide over here. So let me move on to the next 2 slides. Okay, remember, with regards to this, we talked about this before. Anytime you want to see a before and after effect, what you're going to do is you're going to take the equation and you're going to divide the equation by itself. Okay, so I have the master formula written on the bottom right-hand side of this PowerPoint slide. Okay, B is equal to mu times Ni over L. So you take the formula and you divide the formula by itself and you cross off whatever that remains the same. So where's my stylus? Okay, so if the core remains constant, that means that mu2 and mu1 are the same value. They'll divide each other out. If the current remains the same, then I2 and I1 cancels each other out. And if L is the same, then these two cancel each other out. What we effectively have is B2 over B1 is equal to N2 over N1. Okay, so you should be able to see that B is directly proportionate to number of turns. You double the turns, you double the B field intensity. This slide over here, no, you don't need to copy down. Just know the rules of how to solve these problems. You're going to take the formula, and you're going to take the big formula and divide it by itself. That's all you're doing every time. Okay. And at some point, you'll just be able to see what the formula should look like just by looking at the master formula. So this is an example where the number of turns remain the same. So these two cancel out. The length of the solenoid remains the same, so they cancel out. And your core remains the same. So those two cancel out. You end up with B2 over B1 is equal to I2 over I1. Again, I hope you can just see that linear correlation just by looking at the formula by itself. Okay, because at the end of the day, what do you have? You have B is equal to mu, which is a constant, N, which is a constant, L, which is another constant, and you're multiplying by I. So it's just one big fat constant in front equal to I. And that's why B is going to be proportionate to I. So B2 over B1 is going to be equal to I2 over I1 because they are proportionate. Last case. If the number of turns remains the same, so we're going to take the formula and divide it by itself. We're going to divide out the ends because they're the same value. The current is the same value, and the core is the same value. Here's where you got to be careful. Okay, N is for the number of turns. Here's where you got to be careful. A lot of people think that length and B field intensity is proportionate, but they are inversely proportionate. Remember that you have effectively 1 over L in the numerator, and in the denominator, you have 1 over L as well. So when you divide a fraction by a fraction, you're multiplying the first fraction by the reciprocal of the bottom fraction. So what you end up with is L1 over L2. All right, so B field intensity is proportionate to the number of turns. B field intensity is proportionate to current, and B field intensity is inversely proportionate to length. Exactly what you have stated all the way back over here. It's the same trends. Proportionate, proportionate, inversely proportionate. And if you really want to do the fourth one, yes, B field will be proportionate to mu. Any other questions before I move on to my example? Okay, moving on to example number 2. What happens to the strength of an electromagnet if only the current through the coil is increased? Now, for some of you, when you look at this question over here, you probably already know the answer without pulling out a calculator, right? You start off with 1 ampere, and now you crank it up to 2.5 amperes. Well, if you're only increasing up the current and you're leaving everything else the same, if you increase the current by 2.5 times, then the B field intensity, yes, it will increase by 2.5 times. And if this is in the form of a multiple choice question, then by all means, circle the correct answer and move on. Okay. However, if this is a question which requires you to show all your work, then please show all your work. Sorry about all the background noise. Just trying to keep this place relatively clean. Maybe you can stare at my face instead. Here you go. Here's my face. And yeah, if you're wondering how in the world am I able to switch everything all around, this piece of free software, because free is the best, called OBS. Now, some people think that, okay, the software is free, but the hardware is expensive. Well, yeah, if you decide to buy a Stream Deck, I think that's what it's called, then yeah, you can blow $300 off doing that. But you could do it for free as well by using a number pad. Okay, so have all your hyperlinks set up to your number pad numerical values, and you can quickly switch between the screens for free. Another method that is free as well, well, not free, but if you already have it, is if you've already purchased a MIDI piano. All right, so for some of you guys who play musical instruments, maybe you have a MIDI keyboard, maybe you have a MIDI slider, which is what I'm using. You can actually use a MIDI keyboard where if you push a note on the keyboard, it'll switch camera views. Okay, so you could do it that way as well. Anyways, back to this question over here. Okay, I1 is 1 ampere, I2 is 2.5 amperes, and let's go through the long-winded math. You take the formula and you divide the formula by itself. Since number of turns at the beginning is equal to the number of turns at the end, those two values will divide each other out. Since the core was the same, those two numbers will cancel each other out or divide each other out. What else? The length of the turns remain the same, so they divide each other out. So all you're left with is B2 over B1 is equal to I2 over I1. So if you can observe from here and see the proportionality between these two, then yeah, off the bat, you could say B2 over B1 is equal to I2 over I1. And optionally, if you really want to show all your work this way, you could do it as well, but you can see that it takes a whole lot longer to get to the point. Nevertheless, you sub all the values in for what you know. You'll see that the amperes divide each other out because what you're looking at the end of the day is a relationship, all right? What you know is that B2 is equal to 2.5 times B1. Or if you rearrange it, B2 over B1 is equal to 2.5. Hence, the magnetic strength will increase by 2.5 times if you increase the current from 1 ampere to 2.5 amperes. That's how you'd show all your work. Any questions before I move on to the last slide? Okay, last slide then. Okay, so you don't need to copy down the blue variables, but I'll give you guys a moment towards jotting down everything in black, all right? Because again, there's 3 different types of materials. If you read it in your textbook, there are materials that allow, that can become magnetized very easily, like iron, iron, nickel, or steel. Those become magnetized very easily, so they're gonna have a permeability which is gonna be some huge number, all right? And again, you don't need to memorize these huge numbers. They will be some big positive number. So anything that's ferromagnetic will have a mu r, that's a big positive number. If they have a value that's close enough to 1, then they're classified as a paramagnetic material. And if it has a value that's less than 1, which can exist, that means it hates magnetic fields and it wants to run away from it. Gold, copper, and water are 3 examples of diamagnetic materials. I have one last video to share with you guys right now, but just to avoid any form of copyright infringement, this is what the video looks like. And if you want to Google it up afterwards, you're more than welcome to. All right, and you can watch that video there. But I'm going to end my recording right now. So yeah, you just got to jot that down. And your homework for tonight is that course pack page 56, questions 1 through 6. I'll stop the video now, but I'll let that video play after the recording.